Hello everyone. Today I want to present one of our work which is entitled A Federated Multi-Label Feature Selection Based on Information Theory in IoT Environments. So at first I will explain about the main contribution of this work, and then I will explain the purpose method in details. This is the first federated multi-label feature selection in the literature, and we use the information theory concepts as two objectives in a Pareto-based biodirective strategy. And we use the federated learning algorithm and a multi-label classifier for the first time. And we compare the proposed method's results with the 5 other centralized multi-label feature selection on 3 dataset benchmark datasets from 3 different applications. As an introduction, we know that because of the development of technology and many new applications like smart healthcare systems, smart homes, and intelligent transportation systems. And in these applications, there are many smart devices like IoT devices, sensors, robots, that they collect or generate data every day. So these data are collected by these IoT devices. Now what? We need to use these data, these collected data, to use them as an input of a learning model to extract knowledge from the environment or from these data. And but there are some challenges here that these data may contain some irrelevant, noisy, or redundant features, and also these IoT devices may have some limitations, like for example storage limitation or memory limitation, or for example they may have some limitation in communication or computation capacities. So these limitations cause some problem. They may cause, for example, decrease the learning model performance or increase the communication and computation cost. So data pre-processing methods can be helpful here. So among data pre-processing methods, feature selection methods are very popular, and these methods select informative features and remove those noisy, irrelevant, or redundant features, and also they try to reduce the size of the data. So by removing those irrelevant features and just select informative features, we can improve the learning model performance. And by reducing the size of the data, we can improve or reduce the communication and computation cost. So, but in some real-world applications, we may encounter with multi-label data sets instead of single-label data. Instead of having only one single label for each instance, we may have a set of labels for each instance. For example, here you can see the multi-label data structure. If each row is considered as an instance, then each instance has a set of features and a set of labels. For example, in this figure, you can see that there are, for example, if we consider that we have a set of labels that has, for example, 6 labels, like, for example, dog, cat, glasses, cat, flowers, and rabbit. Okay. And for example, for the second image in this figure, the label set should be something like this, because we have dog, cat, and glasses in that image. And so the corresponding label for the dog should be 1, and the corresponding label for the hat should be 0, because we don't have hat in that image. And also for example, glasses and cat should be 1, because we have glasses and cat in that image, but for the flowers and rabbits should be 0, okay? So this is the multi-label data structure. And so here, the feature selection is more important because we need to consider the relationship between the features and all the labels that we have in the label set. So it's more important here to consider this relationship as well. So at first, I want to explain about different feature selection methods, and then I will explain the feature selection methods for multi-label datasets. Feature selection methods can be divided into 2 categories generally: filter-based methods and wrapper-based methods. The filter-based methods, they are independent from the learning model algorithm, and they just use the inherent properties of the feature, like mutual information or correlation between features. And these methods are fast, but because they don't consider the effect of the selected features on the performance of the learning algorithm, they may not be very accurate. But on the other hand, we have the wrapper-based methods. These methods use the feedback of the learning model to evaluate the selected features. So these methods are accurate compared to the filter-based methods, but they may not as fast as the filter-based methods, and they are more complex. And for the multi-label feature selection methods, these methods can be, again, divided into two categories. The problem transformation methods, these methods try to convert the multi-label data into single-label data, and then using those existing feature selection methods to select informative features from the converted data from the multi-label to the single-label. But here, because we may lose some information as we convert the multi-label data into single label, then we lose those correlation between the features and the all labels that we have in the label set. So we lose those information and we ignore those information. So because of that, there are some other methods that we call them algorithm adaptation methods. These methods try to adapt those existing methods to directly handle the multi-label data. So the proposed method here in this work, we consider it as a filter-based and algorithm adaptation method, because we want to have it as a fast method, but at the same time have a good performance at the same time. If you remember, at first I talked about the distributed environment for the IoT environment, that each device collects some data from the environment. Previously, for example, traditionally, we sent all these data from all these IoT devices to the server, central server, edge or cloud server. But because the this edge or cloud server, especially the cloud server, is far away from the IoT devices, so it may cause some problems like privacy issues, or some, as I said before, these IoT devices have some limitations like storage or memory, and also the capacity of the communication and computation. So because of this, another method is proposed in the literature is the federated learning. So in federated learning, we try to train a global learning model without sharing these local data in each IoT devices. So in each IoT devices, we have a local learning model, but we try to train this local learning model by using the local data, and we just send the parameters of these local learning model to the server, to the central server. And then after aggregating these parameters, we update the global learning model, and then we send that aggregated parameters to send back them to the IoT devices. After some rounds, we can have the trained global learning model without sharing these data, this local data in each IoT device. So we just inspired from this procedure of federated learning to propose the federated feature selection. So we just want to select informative features from each of these local data sets without sharing them, and by using this procedure of the federated learning. So here is the overview of our method. We consider two-tier setup. The first tier has the smart IoT devices that collect multi-label data, and the second tier is the edge server. And by using this setup, we just want to answer two research questions. Can we choose the most relevant features while minimizing the redundancy without sharing the raw data? And the second question is that, can we improve the trade-off between the communication cost, computation cost, and the performance of the learning algorithm? So the proposed method has two phases. The first phase is the local phase, which will be in the IoT devices, and the second phase is the global phase, which will be in the edge server. And this method just combine the federated learning procedure and the information theory concepts to select informative features. So here you can see the overview of the proposed method. I will explain it briefly, and then I will explain all the parts in details in next slides. So at first, here in each IoT device, we try to calculate two matrices by using the local data, the mutual information matrix and the correlation distance matrix. And then after calculating these two matrices in all these IoT devices, we send them to the edge server. And then in edge server, we try to aggregate all, for example, the received mutual information matrices from all devices and try to find the global mutual information matrix here, for example, and then we aggregate the correlation distance matrices that we receive from the IoT devices and aggregate it to obtain the global correlation distance matrix. And then we try to calculate the objective functions based on these two matrices, and we try to, using the non-dominated sorting algorithm to find the, to assign to each feature a Pareto number. So for example, here we have the this is the first Pareto front, and the second Pareto front should be the second, for example, here. And this line is the first, for example, Pareto front. And we assign to each feature a Pareto number, and then we calculate the crowding distance for each feature and assign a crowding distance to each feature as well. And by using this Pareto number and crowding distance, we try to sort we assign another score to each feature, S score, and we sort these features based on that S score and send the sorted features, send back them to the IoT devices. So the IoT devices can select informative features without sharing them. So this is the first phase, the local phase that should be done in the IoT devices. So at first, we calculate the mutual information matrix between the features and labels. So we want to calculate it. It is considered as the relevancy metric that we just want to consider the relevancy between features and labels. And after that, we calculate the correlation distance between features because and it is considered as the redundancy measure. And so it's the difference of the joint entropy and mutual information. And after calculating these two matrices in all the IoT devices, we send them to the edge server, and in the edge server we aggregate all these, for example, mutual information matrices and obtain the global mutual information matrix, and again aggregate the correlation distance matrices and obtain the global correlation distance matrix. And after that, we calculate the objective functions because we want to maximize the relevancy between features and labels, and also we want to maximize the correlation distance, which is the difference between the joint entropy and mutual information between features that consider as the redundancy, because by maximize the correlation distance between the features, we can minimize the redundancy between features. And then we perform the non-dominated sorting algorithm, and we assign the Pareto number to each feature, and also we calculate the crowding distance and assign D to each feature. And by using that P, which is the Pareto front number, and D as the crowding distance, we calculate the S score here, and then sort the features based on their S score. And the sorted feature will send back to the IoT devices. So for the evaluating the performance of the method, we consider 6 evaluation metrics: accuracy, F measure, Hamming loss, ranking loss, average precision, and coverage that are very popular in the multi-label data classification. And for accuracy and F measure and average precision, if the number is greater, then it's better. For the Hamming loss, ranking loss, and coverage, if the number is lower, then it's better. And for the comparison methods, we compare the proposed method with 5 other centralized multi-label data set, because this is the first federated multi-label data set, federated feature selection method. And so we compare it with 5 other centralized multi-label feature selection methods. And for example, the PMFS, using the regression and Euclidean distance to evaluate the relevancy and redundancy between features and labels. PPTMI is the problem transformation method that convert the multi-label into single label and then try to select the informative features. And the 3 other methods, PMU, D2F, and SCLS, these 3 methods use the feature, information theory concepts to select informative features. And we use 3 benchmark datasets here for the experiments from 3 different domains. And we use the non-IID or non-independent and non-identical distribution across the clients. And for the experiments, we consider 2 different scenarios here, because the first scenario is a centralized learning scenario, and the second scenario is the federated learning scenario, because in some applications still we may need to send the data to the Azure cloud server for further processing, but still we need to reduce the communication cost between the IoT devices and that server. So we consider that, because of that, we consider the first scenario, the centralized learning scenario. In that scenario, at first we try to select informative features and reduce the size of the data, and then we send them to the cloud or edge server for further processing. So in this scenario, I use the multi-label k-nearest neighbor classifier, which is the most popular classifier in the multi-label papers in the literature, with k equal to 10. And for the second scenario, the federated learning scenario, we just select informative features in a federated manner and also try to train the learning model again in a federated manner. So here I use the vanilla federated learning algorithm with 10 clients and 100 rounds. So here you can see the results. This is for the first scenario that we consider it as a centralized learning scenario, that we at first select the features and then send them to the server or cloud server for training the classifier. So here you can see that, for example, the proposed method with only, for example, 20 features can obtain better results compared to other methods in the literature with 100 features. So it means that if we want to send the data from the IoT devices to the server, if we send it with only 20 features, we can reduce the communication cost, and at the same time we can have the better performance. So we can have good performance with lower communication cost at the same time. And for other metrics like F measure, Hamming loss, ranking loss, you can also see that with, for example, 10 or 20 features, the proposed methods can obtain better results compared to other methods with, for example, 100 features. And this is for the other data set, the BERT data set. Again, for example, in the accuracy, you can see that with only 20 features, we have better results compared to other methods, for example, with 100 or 90 or 80 features. And for the second scenario, that we use the federated feature selection and also train the learning algorithm in a federated manner. Here also you can see that with, for example, for the accuracy with 60, for example, features, it can obtain better results compared to other methods with 100 features, or for other metrics like F measure, Hamming loss, and other metrics, the proposed method with, for example, 20 features can obtain better results. And so here, by reducing the size of the data, we can reduce the computational cost in IoT devices, and at the same time we can have the better performance. So we have a good trade-off between the performance and the computational cost. So, so as a conclusion, this is the first federated multi-label feature selection that try to select informative features and improve the performance of the learning algorithm, so we can obtain a good trade-off between the performance, communication cost, and computational cost. And as you saw in the figures in the previous slides, for example, in the yeast data set, we can obtain better results with only 20 features compared to other methods with, for example, 100 features or something like this.